Hello and welcome. This is Spectacle Explains, where I discuss things scientific. This episode I'm going to be looking at collisions, crumple zones and safety. Well, specifically crumple zones. Just as a background, I'm undergoing cardiac rehab. It's been about a year since I've been out of teaching, and each day I try to produce and publish three either podcasts or video podcasts, and teach for an international audience and actually get some feedback and gradually slowly work up. So this is very much a work in progress. So as I develop more, I'll produce a more sophisticated video. So first off, we're going to have the idea of a car collision. So we have here the wall, and here I have my car, and the definition of a collision. A collision is when a body, this is a body, comes and touches another body. It changes momentum or velocity. What we're going to do is go through and look at the various things that happen. I'm going to do a few things. One is remind you of Newton's first law, and that is a body in motion continues in motion at the same speed and in a straight line unless another force is acting on it. The second law is that a body will accelerate F equals ma. That's an unbalanced force. So I have one force here, a body in between, and if I apply equal and opposite forces to it, or balances forces to it, and the front and back will stay the same. But if I increase the force on this side, it will begin to accelerate this direction. In this case, this is under Newton's first law for the collision. The body is travelling in a straight line at the same velocity before it comes into the collision. So what we're going to do is unpack what happens in collision. In this case, I'm just going to, for your cognitive understanding, go through various stages of collision. We have the wall here. I'm going to demonstrate the car with my hands. And so, in general, what will happen is the car will travel like this, hit the wall, and ideally it will go into a crumple zone, like that, come to a stop. That's not necessarily always that happens, but when it comes into the wall, there is an equal and opposite force. You can feel an equal and opposite force slowing it down, and it undergoes a change of momentum, that is, a velocity times its mass. It goes to here, zero momentum, and then if something else happens, it bounces up, it maintains its momentum and bounces backwards. It changes its momentum, going backwards, the velocity vector. So this way, and now it's going in the opposite direction. So it's had a change in momentum, even though the carrying energy in an elastic collision may not have changed. So let's try and look at this collision a little bit. I want to focus in on the force bit. It's coming in, it begins to see the force. I'm indicating this action or crumple zone that comes to a stop. But I can also equally represent this action where it elastically expands and goes off the opposite direction. The kinetic energy gets changed into potential energy, it deforms, and then reforms, rebounds, and travels off in this direction. So what's happening? This is travelling. This has been thrown off. This hand here is my right hand, but it will be on your left. It will start to drag on, and then it drags the rest of the car with it. Okay, so I might do it again. And let's actually show, imagine there's a force field. Pull my hand away. And the important thing is that it encounters a force when it hits this wall. On this side, a force there. And we're going to do a few equations here. Going back to the original equation I referred to. So Newton's second law is to do with the body. It's all the forces on a particular body. And Newton's third law is a system. It means for every force onto the body puts a force equal and opposite. Their forces are always in pairs. So this force is always encountered by another replacement force. What we're going to go into is a second law, which is F equals ma. So it's going in F equals ma, and it must accelerate. What we're going to do is we're going to multiply. For u, that's F equals ma. We can multiply both sides by time. Force times time equals n, a times time. And a is the final velocity minus the initial velocity in time. So the two times cancel out. So force times time equals m times the final velocity minus the initial velocity. So force times time equals the change of momentum. So what happens is that you can have various things that is coming across the change of momentum to the point that it stops. It can either go like this, or can be like that, ready to rebound, or we can stop it really quickly. It doesn't collapse, it just stops immediately. And in all those three cases, that's crumple zone, no crumple zone and stop, crumple zone in the first half of the collision where it collapses, and then obviously afterwards it's going to expand away and go. The impulse is the same because the change of momentum is the same. It's got the initial momentum m times vi, and the final momentum is 0. And so the change in momentum is, so it's got a momentum in this direction, the change in momentum is in that direction. The two momentums cancel each other, so it's got 0 momentum going across it. So in all three cases, that is no crumple zone coming to a stop, crumple zone coming to a stop, an elastic collision. The first half of elastic collision will stop the camera when it's all sprung up ready to go. It has the same change in momentum, the same initial momentum, final momentum, the same change in momentum. And it also has the same impulse. But in this case, it goes like that, and there's a very large force for a short time. But in the crumple zone, it may take a longer time to decelerate. And so the momentum is the same, but the impulse is the same, the change in the impulse is the same, but the force is very much different. A shorter time, a larger force, or a more gentle force, or a longer time. So a crumple zone changes the maximum force zone encounters, but it does other things. The crumple zone stops the second part of the reaction happening. So even if it goes, say I go like this, that would be a hard thing bouncing back. If this is a car without a crumple zone, it would go like this. It wouldn't necessarily stop, it would bounce back out. So some of the energy, it may lose some energy, but a lot of the energy would be stored in the spin energy of the car and throw it back. And so the actual momentum change is actually bigger without a crumple zone, because the momentum vector, its change in momentum, is not just equal to it. So momentum coming in, the change in momentum is like that. Those comes to 0. It's actually much bigger. So momentum is like this, and it's got a final long momentum from here to here. So you can imagine my momentum vector going that direction. It comes in like this, it goes out with that velocity. So it's changing momentum is bigger. So if it bounces elastically, there's actually not just a higher impact force if it doesn't crumple or deform, but there's also a greater change, a greater overall impulse. I'll just get this going, a greater overall impulse. So let's do this again. So this is Ft is the impulse, and we're going in here. So what happens is that essentially the coming in like this, where it stops, is equivalent to going like this. However, In this case, where it's elastic, if you're supposed to have an elastic car with a rubber bumper on, it would then deform and you'd have twice the impact. So the impact would last twice as long. And what's even worse is that your car, as long as the impact has now become a missile. And say if you're driving with a car behind you, and this car here, this car will bounce back and they'll collide with double the velocity. So it's one of the things is that a crumple zone essentially stops the car and stops the accident. If it was to bounce, if you can imagine a tennis ball bouncing around the traffic, it would all bounce and you'd have basically a chain reaction with everything being bounced. One of the things that the impact zone does is actually throw the engine down into the ground and allows people to continue forward to actually float on top of the engine. The engine can't crash, so the engine is pushed down and you float across. So there's one aspect there. Another aspect is that the crumple zone in a car actually changes the moving energy. Moving energy is going to be changed anyway. It has to. Moving energy has to disappear. It's got to stop. The moving energy has to stop. But it actually pushes it into different channels of energy, which really doesn't matter. You don't really understand it, but it stops it going back into the most important thing is it stops it going back into the potential energy to rebound, sort of a disaster that you want. So the crumple zone does two things. It when you think about it, it reduces the force of an impact. It doesn't, by extending the time, the force, it selects a lower force of a longer time. So that's one thing it does. It stops the car as the second aspect of it. So to stop the car is an important thing because it stops the car bouncing back into the traffic. So there's actually two aspects to crumple zone. Although in school, for some reason, people tend to really focus only on the FT aspect. The FT is the impulse. Mass is a scalar. A vector. Velocity is a vector or a tensor of rank 1. Okay, we'll go into it. But also, the change in momentum and impulse are both vectors because time, it doesn't change what it is. Energy is turns into a scalar, but it's a vector. So the impulse, so I'm going this way. If I go this way, my fist applies an impulse to my hand, but my hand applies an impulse to the fist. So the impulse is a vector, but it is a vector which has only got a short time. Whereas your velocity vector is constant and doesn't vary in time because the first instant impulses are very time dependent. They grow and shrink, and they're very much in that second part of the three parts of the collision, as we've done before. You come in the actual touch and collision, in which it slows to a halt and it can store the energy, and that may be the end of it, or there may be a second part. The second part of the second part where it expands out. This part of the car is thrown with twice the velocity out, and then it's wanted to go, and it would actually pull it out. In fact, if you had a car which wasn't properly made and it wasn't welded properly, what would happen is it would crash and throw out the back of the car twice the velocity. The aim of this is just to practice without preparation. I just sort of sat in front of this car and said, well, I'm going to practice getting back on the track now that I've had my heart fixed up in a whole series of things. My blood's better, everything's much better. To see how I go, I'll have a look at this video, get feedback from a few people how it's going. Thanks for watching. Keep on thinking. Keep on doing science. And so thinking of doing this with your hands. And finally, teaching science, whether you are a teacher or you're just helping your friends, trying to teach them how to get through science. And this is very much Year 11 work called Moving About. You will have to change for sure. Thank you very much for watching.